Why partitioning? There are several applications of least squares adjustment in which either the observation vector or the vector of parameters, or both, are subdivided. In other words, they are partitioned, leading to a better treatment of the problem being studied. For example, the partitioning of the observation vector, L, may result in two vectors, two subset or subvectors, one L1 and the other L2. Vector L1 may be a vector containing old observations in other space or time, and vector L2 may be a vector containing new observations, also new in the sense of space or time. The partitioning of the vector of unknown parameters may result in a vector X that is subdivided into elements pertaining to vector X sub 1 and another vector X sub 2, in which case X1 or X sub 1 may be a vector containing unknown parameters of interest, and the vector X sub 2 a vector containing unknown parameters to which there is little interest in knowing their estimated values, in which case they are called nuisance parameters. Or X1, X2 may be parameters connected to different epochs or to different geographical distribution, which will require solution in steps. Partitioning may also be necessary if additional information besides the information embedded in the observations is necessary to be incorporated. Such additional information may be stochastic or deterministic in nature. Stochastic, in the case of stochastic information, it's often called weighted constraints. In the case of deterministic information, usually called functional constraint. The technique of parameter elimination by partitioning is very appropriate to deal with situations in which we're dealing with partitioned observation or parameter vector. If you look at the, if you consider normal equations, as we usually do, as expressed here in this slide, we have capital N represent the normal matrix. Y in this case would be the vector of parameters. U would be the normal vector, and they're equal to 0, the summation equal to 0. We may have a situation then where either vector L or vector X are partitioned, in which case we need to partition the normal equations, and we end up with this hypersystem of normal equations, matrix, and the normal matrix is subdivided into 4 matrices n1, 1, and 2, 2 in the diagonal elements, and the off-diagonal elements matrix 1, 2, and matrix 2, 1, which would be different. That's not a symmetric matrix. Matrix, vector, the vector of parameters has been subdivided into vector y1 and y2, and the normal vector accordingly subdivided into 2 vectors u1 and u2. We have 2 ways of dealing with it. So we would have to develop the normal equations, which will lead us to 2 equations that we can use to eliminate y1. In other words, we would obtain a solution that would depend on y2 only, or we would be eliminating y2, obtaining then a solution that would depend on y1 only. So in this case here, we get a solution for y2, and there is no y1 term. So y1 has been eliminated, but there is a condition that the normal vector n11 must be regular. Okay, it must be inverted. Alternatively, we can eliminate y2, and we are going to have a solution for y1 totally independent from y2. The condition is that n22 is regular or non-singular, which means it accepts an inverse. Oh, I'll get the color here. Okay, so the hypersystem of normal equations, n11, n12, n21, n22, and we have the partitioned parameter vector y1, y2. I will not underline the elements here. They're all vectors and matrices. Here we have u1 and u2 equals to 0. This is equation 4 in the notes, but I'm going to use a different numbering here. So if we go then and partition these guys, here is what we have. Okay, this is the effect of the partitioning. So doing this, I think it becomes more clear. Now, if we want to develop this system, we're going to have the product of n11 and y1 plus n12 times y2 plus u1 equals to 0. The other term is going to be n21 multiplying y1 plus n22 multiplying y2 plus u2 equals to 0. We can call these equations 1, equation 2. Oops. Equation 2. Okay, here we go. Now let's get a solution. For y1 from equation 1. So what we have then is n11 multiplying y1 equals to minus n12 y2 minus u1. And then equation solution for n y1 is going to be n11 inverse multiplying minus n12 y2 minus u1. This is equal to minus n11 inverse n12 y2 plus n11 inverse. Yeah. Okay, n11 inverse u1. We could basically just write these like that: n11 inverse n12 y2 plus y1. Anyway, these are different ways that we can write. I'm going to call these 3 because I'm going to use this form here. Now we can replace in equation 2. Okay, so replace what? Replace y1. Okay, in equation 2 here. So we are going to have minus n21 n11 inverse n12 y2 plus u1 plus n22 y2 plus u2 equals to 0. Developing further, n21 n11 inverse. So I didn't mention, but it's clear we need to have an inverse for n11. So and when we multiply by n12 y2 minus n21 n11 inverse y1 plus n22 y2 plus u2 equals to 0. So we have y2 here, y2 here. We can then write n22 minus n21 n11 inverse n12 y2 plus u2 minus n21 n11 inverse u1. Yeah, well, if I haven't made a mistake, it's correct. Solution for y2 is then minus n22 sugar. Let me erase this here. This is wrong. Okay. n22 minus n22 n21 n11 inverse n12 inverse multiplying u2 minus n21 n11 inverse u1. That's it. Okay, so here we have a solution of y2, independent from y1. We can have this the opposite. We can generate doing the similar development. We can obtain also a solution for y1 independent of y2. Now, in this particular case, the conditions are conditions are that N11 is regular, okay, or it is non-singular. In other words, N11 inverse exists. The other condition is that the term N22 minus N21, N11 inverse N12 is regular. It has to invert. We have to invert. Otherwise, I have no solution here. So what happens here in practice is that we may have these two parameters, y1 and y2. Okay, and this parameter y1, we may have situations like, example, y1 is of no interest. Okay, so if y1 is of no interest, we can call this equation 4. We can then we can use equation 4 directly. The other example is that we need to estimate y1, sorry, y2 before y1. Okay, so it may be a condition that we have to apply. There are examples. We're going to discuss examples of this particular situation. Both situations actually exist in geodesy and geomatics. So in this case, what we can do is we use dear, this is so ugly. Get out. Okay, we can use equation 4 to estimate y2, then use equation 3 to estimate y1. Okay. There is something else for me to say here now. So here is a mechanics of how we obtain that. Okay, how we obtain the expression. So this expression here, 4, given by 4, can be used. Okay, we will be using to derive expressions for these weighted constraints and the functional constraints. Actually, we can use parameter elimination by partitioning to derive any expression for the solution of these squares. So we did an example here showing how we can get a solution for y2 independent from y1. The similar derivation will be made to obtain a solution of y2 independent of y1. Okay, in which case y1 is not there. Oh yeah, something that I need to emphasize here is the following. If you look at this expression number 4 here, okay, there is no y1 term, but we have information pertaining to y1 here. Okay, so we have the vector u contains observations or misclosures that relate to y1. So these are observations L1. come from observations L1. Elements N1, 2, and of these normal matrix, hypernormal matrix N1, 2, and N2, 2, they also have been fed information that relates to Y1. Okay, so the solution of Y2 happens in this case without having to estimate Y1, but the information that related to Y1 is embedded in the expression. The covariance matrices for parameters C1 and C2 estimated independently is given by this expression we are showing here without derivation. You should realize that you have some associated text available to you. Okay, so just so that you know who these guys are, N22, it's in the text, but I'm going to write in here, N21, N11 inverse, N12 inverse, N21, N11 inverse. M22 is N22 minus N21, N11 inverse, N12 inverse. Okay, so from these guys here, basically solution Y2 equals to M21 Y1 plus M22 U2 if we apply propagation of covariances, variances and covariances to this term. We are going to arrive at this expression here. Okay, and here we have the expression for the so-called back substitution, in the sense that depending on the situation, we may want to estimate Y1. We may want to estimate Y2 first and then estimate Y1. Or alternatively, we may want to estimate Y1 and then estimate Y2. Okay? So please have a look at the notes related to parameter elimination by partitioning. Thank you.